Hey everyone, ready for a deep dive?
That's right.
Today, we're going small,
Really small.
like atom-size small.
Yeah.
We're talking about solid-state chemistry.
You gave us Professor Pedro Camargo's lecture notes on the structure of simple solids. Lots of diagrams,
Those
equations,
shebang.
the whole shebang. Yeah.
But don't worry, we're going to unpack it all.
Make it crystal clear, so to speak.
Exactly, no need to memorize formulas.
Think of it more like solving a three-dimensional puzzle.
Right. Like how do all those atoms fit together?
Yeah, how do they create the materials that we see and use every single day?
Like why do metals shine?
Or how come diamonds are so strong? We'll answer those questions and more.
So if you've ever looked at, say, a metal spoon and wondered what's going on at the atomic level,
This is the deep dive for you.
this is it. Okay, let's start with the basics.
The foundation.
The foundation, yeah.
Yeah.
Why does solid-state chemistry even matter?
Well, I mean, think about it. Solids are everywhere.
Literally everywhere.
From the chair you're sitting on,
To the phone you're using.
even our planet Earth itself.
It's all about solids, baby.
Yeah, and understanding how these solids work at the atomic level.
It's like unlocking a whole secret world.
Right. It's the key to innovation in, well, so many fields. Materials, science, nanotechnology, you name it.
It's like, once you understand the rules of the game,
Then you can start to bend them, create new materials with, well, with crazy properties.
that's what I'm talking about. Okay, so let's get into it. We've all seen marbles, like, jostling for space in a jar, right?
Yeah.
Turns out, atoms in a solid, they aren't that different.
That's a great analogy. They're all trying to get as close as possible, just like those marbles.
So they're like, scooch over, buddy. Make some room.
Exactly.
Yeah.
And that leads to, well, what we call close packing arrangements.
Not just packing, okay.
Yeah, and it's kind of like, have you ever seen those stacks of oranges at the grocery store?
Yeah, like pyramids of oranges.
Yeah, exactly. Each layer nestled snugly into the gaps below.
I can picture it.
So in solids, those atoms want to pack together just as efficiently as those oranges.
Makes sense. Nice and cozy.
Right, and this simple idea leads to two of the most common arrangements in metals: cubic, close-packed, or CCP for short, and hexagonally close-packed, HCP.
CCP and HCP. All right, I remember those. So are we essentially stacking atoms like those oranges in both of these arrangements?
Yeah, pretty much. The key difference is in how that third layer stacks up. See, in CCP, it mirrors that first layer.
So it's like ABC, ABC, kind of like that.
You got it. But with HCP, that third layer, it goes for an ABAB pattern.
Ah, okay. So a slight difference in stacking, but does that really change things?
Oh, you better believe it. That tiny difference has massive implications for a material's properties. Think about it. How tightly those atoms are packed together, that impacts the material's density.
Oh, okay, so denser means more atoms squeezed in.
Precisely. And it can even affect things like, well, like how well a material conducts heat or electricity.
Whoa, so just from the way those atoms are stacked, we can get a sense of how the material will behave.
Yeah. Think of it like comparing a densely packed suitcase to one where the clothes are just thrown in haphazardly.
They both hold the same amount of clothes, but one's way more efficient.
Exactly. And in materials, that efficiency translates to different properties.
Wow, okay. So close packing is kind of a big deal.
Huge. But remember, not all solids are created equal. We've got different types: metallic, ionic, covalent network, and molecular solids.
So 4 main players, each with their own unique style. We've already touched on metals and their love for close packing. What about ionic solids?
Ah, ionic solids. Think table salt.
Salt, okay.
It's all about the attraction between positively and negatively charged ions.
I'm sensing a theme here. Opposites attract.
You got it. These opposite charges, they form strong bonds, giving ionic solids that rigid structure.
So it's less about atoms snuggling up close and more like an electric tango.
That's a great way to put it, an electrostatic dance.
I love it. Okay, what about those covalent network solids?
Now we're talking some serious bonding.
Hit me with it.
Picture a diamond.
Ooh, shiny.
Its hardness comes from a massive interconnected network of strong covalent bonds.
So each atom is like holding hands with its neighbors, forming this unbreakable chain.
Exactly, and that's what makes them so durable.
So that sparkle of a diamond, it's a testament to the power of covalent bonds. That's pretty cool.
It is, isn't it?
Okay, last but not least, molecular solids. What are they all about?
Think ice or sugar.
Okay.
They're made up of distinct molecules held together by weaker intermolecular forces.
So a bit more laid back than those hardcore covalent bonds.
Yeah, more like those atoms are mingling at a cocktail party, Staying close, but not quite forming those deep
I
connections.
can see it now. So they're softer, melt at lower temperatures.
Exactly. They're a bit more chill.
Makes sense.
Okay.
So we've got our metals, our ionic crystals, our covalently bonded networks, and our more relaxed molecular solids. Quite a diverse crew.
It
But no matter what type of solid we're dealing with, there's one fundamental concept we got to grasp: unit cells.
The building blocks of crystals. Think of it like Lego bricks.
Lego bricks. Okay, I'm listening.
Each brick, or in this case, each unit cell, is a self-contained unit.
But you can combine them in endless ways.
Precisely. And by understanding the unit cell, we unlock the blueprint for the whole material.
Wow, powerful stuff. But how do scientists actually visualize these unit cells? We're talking about something incredibly tiny here.
That's the challenge. We're dealing with the invisible world of atoms.
Right. How do we even begin to make sense of that?
Well, scientists use tools like fractional coordinates
Fractional coordinate.
and projections. Think of them like special maps. They help us visualize the 3D world of atomic arrangements, but on a 2D surface.
So it's like taking a 3D model and flattening it onto a piece of paper.
Kinda, but it's more like creating a set of instructions, like a recipe. With these fractional coordinates and projections, we can reconstruct that 3D structure.
Okay, I'm starting to get it, but it
Yeah.
sounds pretty complex. Is this where my brain starts to melt?
Don't worry, it's not about memorizing complicated formulas. It's more like learning a new language.
Like a secret code for deciphering the atomic world.
Exactly. Once you get the hang of it, you can understand the intricate architecture of any crystal structure.
Okay, challenge accepted. Now, earlier you mentioned atoms trying to pack together as efficiently as possible. But is it ever truly a perfect fit?
That's a great question.
Are there ever any gaps in these tightly packed structures?
You're onto something there. Even in the most efficiently packed arrangements, there are always some spaces.
Gaps. So it's not like a solid wall of atoms.
Nope, not quite. We call these spaces holes.
Holes interesting. So even in the most tightly packed arrangements, there's still some wiggle room.
Exactly. And these holes, they play a surprisingly important role in a material's properties.
Okay, I'm intrigued. Tell me more about these holes and why they matter so much.
Well, think of them like secret pathways within the material.
Pathways. What kind of things are traveling along these pathways?
Ions, for example.
Ions. Okay. So those charged particles, they're zipping through these tiny holes within the structure.
They can. And this movement of ions is crucial for things like batteries and fuel cells.
So those little holes, they're not just empty space, they're like the key to better energy storage.
Precisely. They can make a huge difference.
Wow, this is really blowing my mind. We've gone from perfectly packed spheres to gaps and pathways within those structures. And now it seems like these holes are the secret to unlocking new technologies.
That's the beauty of solid-state chemistry, isn't it? It's all interconnected.
Yeah, it's like a whole hidden universe within these materials.
And we're just scratching the surface.
I can't wait to dive even deeper.
These holes, they actually come in a couple of different flavors, you could say.
Flavors. Okay, I'm listening.
We've got tetrahedral and octahedral holes.
Tetrahedral, octahedral. Those are some mouthful names.
I know, right? But they just describe the shapes formed by the surrounding atoms.
Okay, so it's all about geometry.
Exactly. Picture a tiny pyramid.
Okay, I can see it.
That's your tetrahedral hole. Now imagine a diamond shape.
All right, got it.
That's your octahedral hole.
So tetrahedral holes are surrounded by 4 atoms and octahedral by 6.
Yeah.
Like little geometric hideouts within the structure.
Exactly. And the size and number of these holes, well, they depend on how the atoms are packed together.
Makes sense.
Like in both CCP and HCP structures, you'll find 2 tetrahedral holes and 1 octahedral hole for every atom.
So it's kind of predetermined based on that atomic arrangement.
Right, like a cosmic game of Tetris. Everything has its place.
Okay, but I'm guessing these holes aren't just sitting there empty. They must have some impact on how the material behaves, right?
Oh, absolutely. They can act like hidden pathways for ions to move through the structure.
Pathways.
Yeah.
Like a secret network within the solid.
Kind of, yeah.
So what are these ions doing traveling along these pathways?
Well, their movement is crucial for all sorts of things,
Mhm.
like batteries and fuel cells, for example.
Wait, so those tiny holes are actually the key to better energy storage?
In a way, yes. The more efficiently those ions can move, the better these technologies can perform.
Wow, it's incredible how something so small can have such a huge impact.
That's the amazing thing about solid-state chemistry. All these tiny details, they all add up to the big picture.
So by understanding these tiny holes, we can start to design better materials for like all sorts of applications.
Precisely. It's all about understanding the fundamental building blocks and how they influence the overall properties.
Okay, that makes sense. But how do we even know how strong those bonds between atoms are? I mean, we can't exactly take a ruler and measure them, can we?
No, we can't. But we do have a way to quantify that bond strength. We use something called lattice energy.
Lattice energy, okay.
Think of it as the energy released when those ions come together to form a solid ionic compound. It's like a measure of how badly those ions want to stick together.
The higher the lattice energy, the stronger the bond.
Exactly.
So what factors influence this lattice energy?
Well, several things come into play, but the charge and size of the ions are the major players.
So smaller ions, they pack a bigger punch when it comes to attraction.
Exactly. They can get closer together, leading to stronger electrostatic forces.
And stronger forces mean higher lattice energy.
Precisely. This explains why ionic compounds with small, highly charged ions tend to have, well, much higher melting points. It takes a lot of energy to break those strong bonds.
It's like trying to separate two best friends who are inseparable.
That's a good way to put it.
So now when I see salt, I'm not just thinking about flavoring my food, I'm thinking about those strong ionic bonds holding those sodium and chloride ions together.
Exactly. You're starting to see the world through the eyes of a solid-state chemist.
I like it. Okay, so we've talked about perfect packing, we've talked about those sneaky little holes, we've even delved into the strength of those ionic bonds. But what about the imperfections in these crystals?
Defects. Now we're getting to the really interesting stuff.
So those perfectly stacked oranges, maybe there are a few bruised ones in the mix.
Exactly. Even in the most ideal scenarios, there are always some irregularities in the arrangement of those atoms or ions. We call these imperfections defects.
But I'm guessing these defects aren't always a bad thing, right?
You're absolutely right. Sometimes these imperfections can actually be quite beneficial.
Wait, flaws can make a material stronger. How does that work?
Well, one way is through a process called work hardening. By introducing defects, we're essentially creating roadblocks within the material.
Roadblocks.
Yeah, think of it like this. Those roadblocks, they make it harder for those layers of atoms to slide past each other.
So it's like intentionally adding obstacles to make the material tougher.
Exactly. And that increased resistance to deformation, that's what makes the material stronger and more durable.
Wow, that's counterintuitive, but pretty cool. What other tricks can these defects pull off?
Well, some defects, they can act as tiny shortcuts for electrical conductivity.
Shortcuts, how does that work?
Well, in semiconductors, for example, we can intentionally introduce impurities. We call these dopants.
Dopants, okay.
And these dopants, they create defects that allow electrons to move more freely, boosting the material's conductivity.
So it's like adding an express lane to a busy highway. Makes those electrons zip through with ease.
That's a great way to visualize it. And this is how we make transistors and microchips, the brains of our electronic devices.
So it's all about manipulating these tiny defects to control the flow of energy.
Precisely. It's amazing what we can achieve by understanding and controlling these imperfections.
Okay, what about color? Can defects influence the color of a material too?
Absolutely. Some defects, like missing atoms or extra atoms in the wrong place, they can absorb certain wavelengths of light, giving the material a specific color.
So those imperfections are actually what give gemstones like rubies and sapphires their beautiful colors.
Often, yes. It's those tiny flaws that interact with light in unique ways, creating those stunning hues.
So flaws can be beautiful.
Exactly. Now let's switch gears a bit and talk about non-stoichiometry. Have you heard of that term before?
Non-stoichiometry. Sounds a bit intimidating.
It's not as complicated as it sounds. Stoichiometry, well, it's all about that fixed ratio of elements in a compound.
Like a perfect recipe with precise measurements.
Exactly. But non-stoichiometric compounds are the rebels of the chemical world.
Rebels.
They deviate from that ideal formula. The ratio of elements isn't quite what we'd expect.
So they're like, we don't need no recipe, we're going to do our own thing.
Exactly. And these deviations, they can drastically change a material's properties.
So a little improvisation at the atomic level can lead to some surprising results.
You got it. For instance, some metal oxides can become better conductors of electricity when they go off script and become non-stoichiometric.
It's incredible how these tiny variations can have such a big impact. Okay, we've covered so much ground already. From perfect packing to imperfections to even rebellious compounds. What's next?
Well, now it's time to dive into the electronic structure of solids. This is where we really start to understand how those electrons are behaving within a material.
Okay, electronic structure. Sounds like we're going even deeper down the rabbit hole.
They are, but trust me, it's worth it.
Okay, electronic structure of solids. Sounds like we're about to get into the nitty-gritty of how these materials actually work.
You could say that.
Hmm.
It's all about how those electrons are arranged within the solid and how their behavior, well, dictates the material's properties.
Right, because it's those electrons that are responsible for things like conductivity and all that.
Exactly. To really understand this, we use a model called band theory.
Band theory. Okay, now we're really getting into the physics of it all.
It's not as complicated as it sounds. Think of it this way. Instead of individual energy levels, like in a single atom, we have entire bands of energy levels available to the electrons in a solid.
So it's like those electrons have more freedom to move around in a solid compared to being stuck in specific energy levels in a single atom.
Precisely. And the way these energy bands are filled and the gap between them, well, that determines whether we're dealing with a conductor, an insulator, or a semiconductor.
Okay, yeah, those terms are ringing a bell. But how does band theory help us visualize the difference between them?
So in a conductor, that highest occupied energy band, we call it the valence band, it's only partially filled, or it even overlaps with the next higher energy band, called the conduction band.
So there's like an open door for those electrons to move between those bands.
Exactly. Electrons can easily jump between them, flow freely, and that's what makes them good conductors of electricity.
Makes sense. So what about insulators? Are those electrons stuck?
Pretty much, yeah. In an insulator, that valence band, it's completely full, and there's a big energy gap between it and the conduction band.
So like a wall the electrons can't climb over?
A good analogy, those electrons are stuck, making it almost impossible for electricity to flow.
Okay, conductors have that free flow, insulators are blocked. Where do semiconductors fit into all of this?
Semiconductors are kind of the in-betweeners, the Goldilocks of materials. They have a smaller energy gap between those bands, so with a little push, like a bit of heat or light, some electrons can jump that gap.
So it's like they could be coaxed into conducting electricity under the right conditions.
Exactly. And the really cool thing is we can control that energy gap by tweaking the semiconductor's composition.
So we can kind of fine-tune their conductivity.
Yep. And that's the basis for transistors and microchips, all the electronics we rely on.
Wow. It's amazing how all this ties back to those tiny electrons zipping around within the solid.
Right. And this understanding of solid-state chemistry, it's what's driving so much innovation in material science. Scientists are constantly exploring new ways to manipulate the structure and composition of solids to create materials with, well, properties we could only dream of before.
So what are some of those cutting-edge developments? What's on the horizon for material science?
One area that's really taking off is nanomaterials.
Nanomaterials, those are like super tiny, right?
Incredibly tiny. We're talking materials with at least one dimension on the nanoscale, which is like 1 to 100 nanometers.
Okay, so we're talking smaller than a virus. What makes them so special?
Well, because they're so small, they have a huge surface area to volume ratio. It's like comparing a basketball to a beach ball. The beach ball has way more surface area compared to its volume.
Okay, so more surface means more atoms are exposed.
Right, making them super reactive, which can lead to some pretty amazing properties. Increased catalytic activity, strength, conductivity, you name it.
So what are some examples of nanomaterials in action?
Carbon nanotubes are a great example, basically rolled up sheets of carbon atoms arranged in this hexagonal lattice.
So like tiny, strong tubes.
Super strong and lightweight. And they conduct electricity exceptionally well. They're being explored for everything from next-gen electronics and better batteries to new materials for space travel, even targeted drug delivery in medicine.
Wow, so much potential in such a tiny package. What other nano wonders are out there?
Graphene, you've probably heard of it.
I think so, vaguely. Remind me.
It's basically a single layer of carbon atoms in this honeycomb lattice. It's the thinnest and strongest material we know of, plus it's an amazing conductor of both electricity and heat.
So like a single sheet of atoms linked together.
Exactly. And its potential applications are mind-blowing. It could revolutionize everything from electronics and energy storage to sensors and water filtration.
It's amazing to think that by understanding these tiny building blocks of matter,
Yeah.
we can create such incredible things.
Right. And this is just the tip of the iceberg. There's so much more to discover in the world of solid-state chemistry.
Well, I've got to say, you've given us a lot to think about today. We've gone from perfectly packed oranges to those sneaky little holes and even rebellious compounds that break all the rules. And then this whole world of nanomaterials with all their incredible potential. It's amazing to think that something so seemingly simple as a solid can be so complex and fascinating.
And so crucial to shaping the world around us.
Absolutely. So to all our listeners, keep exploring the world around you. Who knows what incredible secrets those solids are hiding?
And remember, the journey into the heart of matter is just beginning. Keep those atoms close, and your curiosity even closer.
That's right. Until next time, happy exploring.